right, AP physicists. We took a little too long getting through this, and this cold just got the better of me. So we're just going to do it this way today. Here's my if chart from yesterday, and I've gone through and I've calculated the area of each rectangle on here. So for this green one, I get an area of 0.12 kilogram meters per second. And for this red one, I get an area of negative 0.0336 kilogram meters per second. And over here for the green one, I get 0.53 kilogram meters per second. And for this red one, I get 0.23 kilogram meters per second. The boxes have different masses. So unlike trials 1 through 4, they're not just swapping. They're not just swapping their speeds, I should say. So these areas don't have any real obvious pattern, but if I total them up, the initial total area is 0.086 kilogram meters per second, and then the total of the final, so I'm taking 0.53 plus 0.23 here, and that doesn't look right. Let me double check that. What did I say here? 0.53 plus 0.23. There we go. It's even worse than that. I think 0.76. All right. Kilogram meters per second for the total over there. So I don't know that anybody's going to be too convinced that there's an obvious pattern there, but had we had everybody's boards together and looked at them in total, it becomes kind of evident that, well, the total area for the boxes over here and the total area for the boxes over here, they're pretty close. And in some of them, in fact, they're going to be equal. And that's the idea that we're aiming for here, is that whatever the total initial area is, the final total area, we hold that same amount. And then what we're looking at here in kilogram meters per second, and we talked about this in pretty much every class, you're taking the mass, I keep trying to use an X there, I don't want to be, mass times velocity, and that's giving us something that we're going to call momentum, okay, or MV. And again, the units you're taking kilograms times meters per second, and that's going to be equal to the unit for momentum, which is kilogram meters per second. That is different from kilogram meters per second squared, which you'll recognize as the Newton. The difference there, amongst other things, is you're taking mass times acceleration to get that, and that gives you the unbalanced force. But they're similar, right? What do I got to do in order to get that unit for the Newton to become the unit for the momentum there? And we can kind of get at that through this equation. So keep in mind that acceleration is the change in velocity divided by the change in time. And so all I'm going to simply do here is rearrange this, and m times delta v, if I multiply both sides by that time interval, on this side I'm going to have unbalanced force times time interval. And so the result kind of makes sense. If I apply an unbalanced force to an object for a period of time, the mass is going to have a change in velocity. The greater the time interval I apply that force, the greater the change in velocity. Or if I increase the force that I'm applying and I don't change the time interval, I'm still going to get a bigger change in velocity. If I expand this, it's mvf minus mvi equals fu delta t. And we just said over here, mass times velocity equals momentum. So this is the final momentum for an terrible F. Final momentum for an object minus the initial momentum for the object is equal to unbalanced force times time, okay? So an object experiences a force for a period of time, its momentum is going to change. That is important then to take back up to the lab and look at not the total area on each side, but look at the change, okay, for each object. So what is the change for the red? What is the change for the green up here? If I do that real quick, let's see. I'm going to have red final is 0.23 kilogram meters per second. Red initial was negative 0.0336 kilogram meters per second. So I'm going to get a change there. 0.23 minus 336. I'm going to change of positive 0.26 kilogram meters per second. And I do the same thing for green. Final for green. Let's change that color. Final for green is 0.53 kilogram meters per second. And the initial for green was 0.12. That doesn't seem right. Something's amiss there. Let me double check that. Mistakes being mandatory and whatnot. All right. Needing to change these quick. That's not 0.23. That's 0.023 kilogram meters per second. This is 0.053 kilogram meters per second. So we're going to change this to be 0.023 kilogram meters per second. That's going to change this. Total shouldn't have been 0.76, should have been 0.076 kilogram meters per second. Still not the same thing as this, but a little more reasonable. Now if I calculate the change for the red, 0.023 minus negative 0.0336, 0.023 minus 0.0336 negative 0.023 minus 0.0336. All right, there we go. 0.056. 0.056 kilogram meters per second. And this is going to be 0.053 kilogram meters per second minus 0.12 kilogram meters per second, and 0.053 minus 0.12 negative 0.067 kilogram meters per second. So they're not perfect, but for some of you it'll work out pretty nicely. And if we had that all displayed up front together, probably would have eventually bought a pattern that says that these are pretty close to the same magnitude. They're not terrible, right? If I just go ahead and round this up to 0.06 and then kind of forget about the 7 on here, then, hey, that's kind of how that works. This is 0.06 kilogram meters per second. This is in the 0.06 kilogram meters per seconds. But this one's positive and this one's negative here. What's going on? Well, again, during the collision, prior to the collision, each glider is going to have FG and then the smoosh poosh with the air cushion. And for these, I shouldn't draw those so similar. The red's got smaller FG and smaller smoosh push from the air cushion. But then the thing that's going to cause the momentum to change is they're going to smack into each other, okay? So if this is red and this is green, green's going to feel a force that way, smoosh push. Green feels it, red deals it. And red's going to feel a force that way, smoosh push. Red feels it, green deals it. And those have to be the same size because, well, they are a force pair, right? Red comma green, green comma red. So we're locked into this thing, provided that these are the only two forces, or I should say, provided that the only forces involved in the momentum change are interactions internal to the system, just green acting on red. And then apparently in this case, we probably had a little bit of banging off of the track that would have scraped off a little bit of velocity somewhere. And that's why I ended up with a little bit less total momentum in the end. But generally speaking, if it's a really nice collision in that the only interaction is occurring between the two objects, and not with anything else, then, well, yeah, the force that this one feels is going to be the same magnitude as the force that this one feels. They're going to be acting for the same amount of time, so they're going to experience equal and opposite changes in momentum for that reason, okay? So this whole unit that we're going to be diving into here is just an extension on that idea that that forces come in pairs, okay? So again, what you're looking at here is a change in momentum. And then this side over here, when we're talking about the product of unbalanced force and time, that's called the impulse, okay? And one thing that I like that I saw in the book, in between the I and the F, they have another one, and it's like a force versus time graph. So these are velocity mass bar graphs. And then in between there, they have this force versus time graph. And the bar that you get there, or whatever it is there, let's say it's a constant force acting for a period of time. Boop, 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 boop. Well, this rectangle here, that's going to be, this would be unbalanced force. Product of unbalanced force and time, that's the area of this rectangle here. So the area of this graph, which is force versus time, is going to be equivalent to what we're getting on the velocity mass bar graphs. Wait. That's velocity mass. That's kilograms times meters per second. This is force and time. That's newtons and seconds. But keep in mind, kids, newtons, oh, it's on here somewhere. Newtons are kilogram meter per second squared, okay? So if I take a kilogram meter per second squared and multiply that by seconds, I'm going to get rid of that squared. I'm going to get left with kilogram meter per second. So those are equivalent units, Newton seconds and kilogram meters per second, okay? Let's hope that's basically all you're going to need in order to deal with the problem set today. Look for a mastering over the weekend if I can get internet restored at my house, which is to say, probably look for it on Monday. And yeah, have a great weekend. We'll see you later.